Right, the first one. A pendulum starts at its amplitude. It's swinging back and forth. It swings 5 centimeters either side. It takes 2 seconds for each swing. How fast is it traveling after 5 seconds? Okay, so what's happening here is you have a pendulum and it's swinging back and forth. So the amplitude is 5 centimeters. I tell you the time. The time is 2 seconds. And I think we have our formula. Omega equals 2 pi over t. So that means omega is equal to pi. So omega is 3.14 radians per second. That's the omega. And you also have, and the A is 0.05. And you also have the formula V equals A omega sine omega t. So after 5 seconds it would be 0.05, 3.14 sine in radians, 3.14 multiply 5. So in radian mode, please, what do we get for the V? Please tell me. You have a calculator. Are you in radian mode? 0.025 meters per second, or if you want 2.5 centimeters per second. Alright, that was question 1. Number 2. A 50-gram mass is put at the end of the spring. The spring's at rest. The guard pulls down the spring a distance of 10 centimeters and releases. So what's happening here is there's a spring. The guard pulls it down a distance of 10 centimeters and it starts to move up and down. So the amplitude is 0.10. The time is 0.75, which means the omega is 2 pi over t, which is 2 pi over 0.75. Yeah, what's that, please? Don't look at me. Type it in. What is it? No, it's not. Is it? No, that seems way too big. Thank you. 2 pi over...
Not in the written one.
Oh, you're right, KJ. I apologize. 8.38. Thank you. Radians a second. Okay, so the first question I've done, find the omega. Second question is, what's the acceleration after 1 second? So I gave you a formula. What was it? A equals minus omega squared s or x. Doesn't matter whichever you want to use. I feel like using x. Did I give you the other formula for acceleration?
Yeah.
Did I give you this formula? A equals minus omega squared a cos omega t. Did I give you this?
No.
But did I give it to you? Well, actually, you know what? Even if I didn't give it to you,
It's the same thing.
yeah, you know what the formula for x is. It's a cos omega t, isn't it?
Yeah.
So you can just put that in there and get this formula. A equals minus omega squared a cos omega t. We know that the t is 1. So let me see. Radian mode. Minus omega squared times a times cos omega times 1. So I got acceleration of 3.51 meters per second squared. So what's the force F? Oh, and this is a positive. F equals ma. So multiplied by the mass is 50 grams. So I get 0.175 newtons. Is this force upwards or downwards? The answer is up, because it's positive. And lastly, what's the force in the spring? It might look like this is the same answer as part 3, but it's not. If I go down, I can draw another picture for you. Right now there are two forces on the ball. The first force is from the spring, and the second force, what do you think this force is here? What's the downward force? mg. Yes? So, this answer here is not this, it's not this, it's actually the total, the net.
Sir, what's
Yep.
the good with the solution of it?
For which one?
The solution.
I got 3.51. Are you in radian mode?
Yeah.
Is that 3.51? I'll double check it, okay. 2 pi, what did you get for omega?
8.33.
Yeah, okay, so omega squared times a, what's the a?
0.1.
0.1.
Yeah.
I still got 3.5 here.
Yeah, I think.
Yeah, okay, continue, yes. So this is the total force on this system. So in fact what you have is F total is spring force minus mg. So you have 0.175 equals spring force minus mg. So the force in the spring is actually 0.175 plus mg. So that comes in at 0.666 newtons. Okay, can I go on? Yep. The next one, the train has a soft bumper, and the bumper is, you know, like a car bumper if you bump into something. So when the train is parking, its bumper hits the wall. So this is what's happening. Here's the train, and the bumper hits the wall, and then the bumper compresses. So the bumper hits the wall, it compresses a little bit, and then expands. Right, so I say it compresses a distance of 2 centimeters. So that's like the amplitude is 2 centimeters. And the time, what's the time here? Well, in the question I said it's 250 milliseconds, which means the time is 500 milliseconds. Now, can anyone tell me why I multiplied my answer by 2? Yeah, that's it. It takes 250 milliseconds for the bumper to compress. Therefore, you'll say it takes 250 for it to decompress. So the time is for one full cycle. So we have to multiply our answer by 2. So I have the A and I have the T. And I want to know how much energy is stored here. So I think the formula for the energy, what did I say it was? It was omega squared x, wasn't it? No, yes, no. Formula for the energy? A half omega squared x, wasn't it? Can you check it?
Yeah, no, half m omega squared x squared.
Oh, sorry, I forgot a half m
Omega square
omega squared
S
S
square.
s or x squared,
squared.
yeah.
Yeah, yeah.
You sure about the m here?
Yeah,
Yeah.
that's it. That's right.
Okay. Yes, of course the m should matter, because the bigger the spring, the more energy it'll have in it. So anyway, I know the x, here it is here. I don't know the omega, but I can easily find that. Omega is 2 pi over t.
That's amplitude, not S.
Yeah, but it's s here because we're looking at when it's fully at its amplitude. Fully decompressed? Yeah. I'll show it to you now in a minute. The omega is 12.57 radians a second. If you think about it like this, there's like a spring in here, and here's the spring compressed. So this is the formula for the energy in the spring when it's compressed by a distance of x. So when the x is a, that means it's fully compressed. That's the maximum energy it could have.
An amplitude.
Yeah.
Okay.
It's also, you can think about it like this, the energy it'll have here, well no, actually just think about it like that, yeah. The x is how much you compress the spring. So the most energy it can have is when it's fully compressed, which is what happens in this picture, and that's when the x is equal to the a. Maximum compression. Yeah? I didn't do an example like this in class. Okay, so let me just type the numbers in. Squared divided by 2 times 0.02 squared. So the energy is 0.03 m, whatever the mass is of the bumper. Well, I suppose it's not just the bumper actually, sorry, it's the whole train. So, for example, how big would a train be? Oh my goodness, 100 tons? I don't know.
No.
Bigger? Yeah, probably 1,000? 10,000? Maybe 10,000. So if the mass is 10,000 kilograms, for example, then the energy stored in the bumper,
10,000 kilograms.
yep, times 0.03. I think it might be more than 10,000. 100,000? Yeah, let's say 100,000. Then the energy will be 3158 joules. Okay. And this energy in the bumper, where did this energy come from? Anyone know? Where do you think this energy came from in the bumper?
Reaction?
Huh?
The reaction in the.
No, not this. What form was this energy in before it became potential in the bumper?
Kinetic.
Kinetic of what?
Moving.
The moving train. Because if you think about it, the train was moving
Yeah.
and had its bumper, and then bumper will hit into the wall and it will slow it down and bring it to stop. So it has kinetic energy here, but when it's stopped it has no kinetic energy. So all the energy is stored in the bumper as potential energy. And then what would happen is the bumper then opens back up and then the train starts moving backwards after it hits the wall. So it moves in, kinetic, 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 potential, and then back to kinetic. Okay. Last one here. You have a spring and its frequency is 2 Hertz, which means its time is 1 over f, which is 1 over 2 seconds. Its omega is 2 pi over t, which is going to equal here 12.57 radians a second. And what am I looking for? The velocity. So I want the velocity, so I need A omega sine omega t. I tell you the A is 10 centimeters. The omega is 12.57 and the time is after 2 seconds. So I have 0.10 dot times dot. Okay, so yeah, if I just put all of this into the calculator, I get that was silly. I get 0. Why should I know it should be 0 though? No, you shouldn't be able to know. You can actually tell without doing this calculation that it should be 0. Why do I know it should be 0? Anybody? Come on. Somebody must know. No need. Nobody knows? Nobody knows? What's the periodic time? 2 seconds. Half a second.
Yeah.
Yeah? So, after t equals 2 seconds, that's equal to 0.5 plus 0.5 plus 0.5 plus 0.5. That's equal to 4 cycles. So after 2 seconds, where will the spring be? We'll be back at the start. After 2 seconds, the spring went like this. You hold it down, it went up, down, up, down, up, down, up, down. After 2 seconds, it's back at the start. What's the velocity at the start? 0. Because the girl pulls it down and holds it. So it's at rest at the beginning. So I knew it should have been 0 actually from the times. So it is definitely 0 here. So I'm actually, in fact, I forgot I did this question on purpose to make it a trick. You didn't actually need to do any calculations for this. If you read it carefully, you'd figure out that it should be 0.
Just then we told that amplitude is 0.1.
Yeah, I tell you the amplitude is first 0.05 and then later 0.10. That's also there to confuse you. Changing the amplitude does not change the omega. In fact, changing the amplitude here changed nothing because the time is the same. So the only thing that mattered here was the fact that this was half a second. Because this is half a second and this is 2 seconds, it makes this 0. It doesn't matter what the, in fact I didn't need to use the A here. I didn't use it anywhere. So I just put that in as a confusing oh, I wrote it down, but I didn't need to use it. Like, where is my A here? I don't see it anywhere, do you? Yeah, because I didn't need it. Oh yeah, but my point is now, I didn't even need to do that. I just needed to know this and this. Because of that was enough. I didn't need to know my A. Yeah? Come on. Did you write this down? Yeah? So we'll do the next worksheet now. Where's your notebook? Ah. Okay. Can I do the next worksheet now? Yeah.